Could forces only become unruly in extreme environments like black holes? Or is there a completely opposite type of extreme terrain in the universe? One where all forces are nearly muted? In energy filament theory, if the energy sea could be torn into a black hole-like funnel, then it is only natural to ask, should the same sea also allows for the existence of tension mountain bubbles, regions of extremely low tension that barely transmit energy? From the perspective of forces, we might temporarily call these regions quiet holes. The boundary of a black hole is fairly straightforward to understand. It's like a sharp drop into a canyon. As you move deeper, the tension grows, and the slope becomes steeper. Anything crossing that threshold is pulled toward the bottom by gravity, where forces become nearly uncontrollable. However, the boundary of a quiet hole is the exact opposite, a steady rise in elevation. Compared to the surrounding universe, this particular area would have much lower tension. The slope here would point in the direction of leaving our familiar region, and the outcome of anything inside this area is that matters will gradually slip toward areas with higher tensions, driven by the forces at play. As a result, almost nothing would want to remain in this high-energy region for long. Over time, this area would either remain empty or contain extremely sparse traces of matter. The interior of a quiet hole is not a complete void in the traditional sense, but it is a space where the forces of the universe operate in a highly subdued manner. The rules of the four fundamental forces are still formally in play, but the tension is so low that transmitting energy through this space is a great deal more difficult than in normal regions of the universe. Gravity, for example, would still exist in the form of a slope, but moving a particle along it would take many more orders of magnitude longer than it would in the normal universe. Electromagnetism could still carve out texture patterns, but it would be extremely difficult for any charged structure to make a notable response within this environment. As for the strong and weak forces, processes such as map filling and reorganization would almost be impossible to realize, as there simply wouldn't be enough particle structures present to make these forces operate effectively. A more subtle point to consider is that, from the perspective of the energy sea itself, if the quiet hole were to remain completely still, it would eventually be leveled out by the surrounding tension flows. For a quiet hole to persist over time, it could not be a stagnant, motionless region. Instead, it would likely exist as a large, spinning bubble formed by the energy sea itself. This spinning motion wouldn't just involve small particle circulations, but there would be a macro-level rotation of the entire bubble within the sea. The spin of the quiet hole would be an essential feature to help it resist being flattened by the external forces at play. For forces in light, the outer shell of the quiet hole presents a very unique boundary. To maintain its loose inside, relatively tight outside structure, this shell must possess a steep gradient in tension. When viewed from a distance, the quiet hole will not appear as completely transparent or void-like, as if there's nothing there. Much like a black hole, the quiet hole will still have a distinct lensing effect on light. Light filaments traveling through this region will need to bend around the tension mountains, following the easiest path of least resistance. However, the way the quiet hole distorts light will differ from a black hole's funnel-shaped distortion. Instead of bending around a valley, as a black hole would, the light would bend around a peak in the case of the quiet hole. It's important to emphasize that the concept of the quiet hole is currently just a prediction derived from the forced terrain logic of energy filament theory. If we accept that black hole valleys can exist within the same energy sea, then it seems only natural to predict the existence of unobserved tension mountain bubbles, vast regions of very low tension, spinning rapidly with extremely low material presence, acting as areas where forces are nearly silent. The tension gradient of the shell surrounding a quiet hole, the lensing effects on light passing through, and whether such regions could leave identifiable signatures in future cosmological observations are more detailed questions that we'll save for a future season dedicated to these concepts. For now, what we do know is that these quiet holes could represent a completely different kind of cosmic terrain, one that challenges our existing understanding of how forces and energies behave. Tap follow, share it on New Physics, click nuclear universe.